Hi everyone. Today our topic is the square root parent function. So you may be wondering, why are we talking about a square root parent function, this new parent function, when we just had a conversation about inverses? And it kind of seems like we're jumping around here. Well, we talked so much about quadratic functions and parabolas, and then we jumped to inverses. And the reason that we're discussing the parent function now is because it kind of marries those two topics of quadratic functions and inverses. So the square root parent function is the function that is the simplest square root with an x. So f of x equals the square root of x. You could also say y equals the square root of x. That's a nice simple equation that still describes the square root parent function. And in order to really discuss the key features of the square root parent function, we need to talk about its table values. Its table values and the graph of the square root parent function. Now, just like any other function, in order to generate a list of x and y values, you pick some x's, which I've gone ahead and done here, and you'll notice in your notes you have some y values over here. Those are incorrect. So if you will just go ahead and mark those out, so that they're not there anymore. Those are not the y values. Those are just y values from a different problem that creeped their way into the notes today. Got into the notes today. So in order to find the y values for this list of x's that I've supplied you with, you need to do the process. The process is the square root parent function. All the y values will equal the square root of the x value. So here, if I take an x value of 0 and I square root it, well, the square root of 0 is 0. My y equals the square root of x. Same thing for the next one. If I square root my x value of 1, the square root of 1 is 1. So y equals the square root of x. Next up, y equals the square root of x, which is 4. The square root of 4 is 2. So 2 equals the square root of 4. Y equals the square root of x. So I'm going to continue finding my y values. And now notice that I have several sets of ordered pairs that I can plot on my graph. Now my graph is not giving me a y-axis and an x-axis in the middle of the graph. Notice that my y-axis is all the way over here and my x-axis is all the way at the bottom. That means that this is quadrant 1. We're only showing quadrant 1 for our graph, because the parent function only fits in quadrant 1. So if I graph my ordered pairs, 0, 0 is the origin. That's all the way down here. 1, 1, right here. 4, 2, so 4, 2. 9, 3, 9, 3. 16, 4. And then 25, 5, I can't fit on here because my graph only goes to 20, but I get the idea that this is my square root parent function. Now, I'd like for you to just think for a moment what it kind of looks like. Even if I turn it this way, think about what it kind of resembles. And just hold that thought to yourself. What does it resemble? What does it sort of look like? Now, some key features of this parent function are that it has a point at 0, 0. Dare I call it the vertex? So a vertex at 0, 0. It's increasing. And it sort of resembles a what? It resembles part of a horizontal parabola. Resembles part of a horizontal parabola. If I were to extend this down here and then go back to the right, it would be a horizontal parabola. So I'd like for you to keep this in mind whenever we move to our second page of the notes today, because in the second page of the notes today, we're going to discuss the square root function a little bit more in depth. And notice that I have underneath the title that it is the quadratic inverse. So just a reminder that the quadratic parent function is f of x equals x squared. It has a vertex at 0, 0, and you use the quadratic pattern to generate the other points on the graph. So over 1 up 1, over 1 up 3, over 1 up 5, over 1 up 7, and so on the other side of the graph as well. Now I've supplied for you a list of ordered pairs for the quadratic parent function. So negative 3 comma 9 is right here. Negative 2 comma 4 is right here. Negative 1 comma 1. 0, 0, 1, 1, 2, 4, 3, 9. So I'd like for you to take a moment, pause your video, and I'd like for you to switch x and y to create the inverse of the quadratic parent function. Remember, in order to identify the inverse from a table, you just take your x and your y values and you switch them. So take a moment to fill in the table for the inverse. Pause your video. So check your table values with the ones that you see on your screen now. All we did was simply take the x column and make it the new y column. We took the original y column and made it the new x column. So now I have a completely new set of ordered pairs that have been generated by performing an inverse, by switching the x and y. So I'm going to go ahead and take these points and plot them now. So 9 comma negative 3, 4 comma negative 2, 1 comma negative 1, 0, 0, 1, 1, 4 positive 2, 9 positive 3. So here's my inverse of the quadratic parent function. Now this new graph, still a parabola, but this new parabola is not a function. This parabola is not a function because if I were to draw some vertical line anywhere that intersected a point on the graph, I would find that it intersects the graph 2 times. So this is not a function. Because not only does this does this fail the vertical line test, but we could easily check to see if the inverse were going to fail the vertical line test by seeing if the original function passes or fails the horizontal line test. So notice that it fails. So its inverse is not a function. Remember that graphically, in order to find the inverse, you would take this and you would reflect it over the parent function, the linear parent function. So it should look like this. So the new graph is not a function because the original function fails the horizontal line test, which means that the inverse function is going to fail the vertical line test and not be a function. If the inverse, though, if this graph is limited to only the positive square root values, so only the positive square root values, all of these negatives that are right here, if I take these and I ignore them, that means that I'm taking this block, so this entire portion of the graph, I'm going to forget about. Now if I do that, I'll notice that if that inverse is limited to the positive square root values, then a square root function would be created. So this bit of the graph is an exact match to what we had on the previous page, the square root parent function. So the reason that we discuss the square root parent function after we discuss inverses and quadratics is because the square root parent function is the inverse of the quadratic parent function. We just ignore the bottom part so that it can actually be a function. So at the bottom, you'll see some of the key features of the square root function. So you can either write it as y equals the positive square root of x, or f of x equals the square root of x, just like we had on the previous page. Some of the key points are the origin, 1, 1, 4, 2, 9, 3. Those are some easy points that you can plot on most coordinate grids. The domain, all the x values, have a boundary right here at x equals 0, but they'll continue on forever to the right. So your domain is all the real values from 0 to infinity, or all the x values greater than or equal to 0. And then the range, bottom to top, has a boundary right here at y equals 0. But again, it will continue growing. So your range goes from all the real values from 0 to infinity, or all the y values that are greater than or equal to 0. So this is just a little introduction today about the square root parent function and why we discuss it, because the square root parent function is the inverse of the quadratic parent function.